We live?
I don't know.
It was not clear.
We are live.
We are live. Okay, everybody, welcome back. Next up, we have Konstantinos Meichanetzidis talking about QNLP for NISQ devices.
Thanks, Alex, and thanks to the organizers for such a cool conference. This talk is featuring these smart people over here. Bob, Alexis, Giovanni from Oxford and CQC, Stefano from CQC and Hashberg, and Nicolo from Hashberg. This talk is about fleshing out this slogan that I just made up, from word to sentence to diagram to quantum circuit, which is basically, expanding on Lambeck's book title, From Word to Sentence. And this is the whole pipeline, high-level view of the paper that we wrote. And this whole talk is about taking you through these arrows that are drawn here. So we start from a sentence, which is some part of some data corpus. It's a parser gives it types, grammatical types. From that we create a diagram that lives in a grammar category. We reshape and manipulate the diagrams. We get a new diagram, B prime, and then we put flesh on that diagram, which we treat as a skeleton, and that flesh lives in finite Hilbert spaces, and we use that space as basically an arena where we encode the semantics of that sentence, and then since we encode it to Hilbert spaces, we find we try to find suitable ways to send these meaning states of sentences onto NISQ devices. And we do this with the help of transpilers that are very simple or more complicated compilers that basically are architecture aware. So I'll take you through the whole setup with examples. I think that's easier. So here's a grammatical sentence. Ross draws snaky spider. Now, first, I said the first step is that a parser comes in and solves the easy problem of assigning grammatical types so that this sentence parses just to the sentence type. These are pre-group types that are assigned to each sentence. And you see that there are two inverses, a right and a left one. And N is a noun type, and S is the sentence type. So you see the inverses annihilate. The right annihilates the noun from the right, the left inverse annihilates the noun from the left, and only the S type survives. So that was the grammar reduction, and from it I say that I'm going to replace all the words with some triangles, some boxes with triangular roofs, and they will be states. And the grammatical reduction that I showed you before will be replaced by some compact structures of this finite vector space category. And basically what I'm trying to say is that these are states, and the grammar assigns these wires connecting the states, and these wires carry some dimensional Hilbert space where the dimension of the wire depends on the type of the pre-group type that the parser assigned before. And basically what I described was the disco-cut model that was introduced by Coecke, Mernouche, and Stephen Clark. And basically, in a slogan, what's going on is words go into the grammar, word states go into the grammar is the piping, and the piping prepares the meaning state of the whole sentence. So it's a compositional model of meaning for natural language. And this talk is about how we take these sentences, the meaning states for sentences, and put them onto quantum circuits. So the inspiration for it was from this paper by Zeng and Coecke, where for the finite vector space that plays the role of the semantic space, they chose the finite Hilbert spaces, and so these states are quantum states, and these cups are just Bell effects. They're post-selection on Bell states. And you see that only one wire survives, and this wire basically says that the whole thing is a huge vector that lives in dimension 2 to the ns, where ns is whatever many qubits we're using to encode the meaning of the whole sentence. And this is basically what's behind the slogan of Bob language is quantum native. We're taking advantage of the product structure, the tensor product structure of quantum theory, reflects the product structure, the compositional structure of pre-good grammar to construct meaning states as quantum states for grammatical sentences that obey pre-group grammar. So before we go to quantum circuits, I'm going to show you how we can manipulate the diagrams to be a bit more friendly to the architectures. So first of all, we're going to do a reshaping, which is done in the also on the original paper by Zeng-Coecke. And basically what you do is you try to remove these cups, and you do that by flipping these states, some of the states, to effects. So this was done by, well, expanded on Zeng and Coecke's paper, and it was done by Stefano and Nicolò. And what they did is they used the transposes to create some bipartite graph for generic pre-group parsing. And if you add swaps, you can do it for any sentence I give you. And they also created this GitHub repo where code will be uploaded soon that does this for any parsed diagram. Another reshape is what Alexis and Giovanni did using Antonen's work, where basically you don't use transpositions to remove the cups. What you do is you take every state that has at least one adjoint type, like a right or a left in its typing, and you replace it with a box, and with the help of these cups here, now there's no adjoint types, right? So this NR became this N, and this NL became this N. And with these cups here, we removed any adjoint type from the diagram. So this is basically using process duality. And what you can do then is just yank the wires, just remove the snakes, and they also uploaded code on this GitHub repo, and there's a toolbox they created called DiscoPy. And what Alex and Giovanni also did was they used this framework to also play with Wittgenstein's functorial language games. So if you want to see how this is applied, go and check this paper by them. I'm going to go back and show you that there is a difference, right? Here I got this diagram by the first method. Here I got this diagram from the second method. It's the same sentence, but it's just different ways to reshape them and prepare them and put them, let's say, in circuit form. So now that we've combed diagrams, let's recap. What we did was we just started from a parsing. We used the parsing as a skeleton. We put meat on the skeleton to be the meaning state of a sentence. And then what we do is ask what is in the box, right? If I specify you how to create these boxes, how to construct the states from these boxes that I was drawing before, then you have a blueprint, a template to send it to quantum circuits. So as I said, any state is basically a preparation with a box, with a process from some trivial state. With this lollipop, I'm using the ZX notation to basically symbolize interpretation. Tensor interpretation is basically just the zero state going in. So I have a bunch of all zeros going in, right? And some process prepares the state of a word. So you can think of every word in that sentence that I showed you basically being represented by a bunch of different parameters. So what is in that parameterized box that I showed you before? Well, let's pick an ansatz for it, as we do in quantum machine learning style. So here I am showing you an example of IQP ansatz. They're called IQP. It's called instantaneous quantum polynomial. Basically, it means that I have a bunch of Hadamards here, making turning the zeros into a bunch of plus states, right? And all of these plus states, then they go and they they go through these controlled Z phases. So this thing is a controlled Z rotation. Because all of these are controlled Zs, it's a big diagonal transformation with a bunch of thetas on the diagonal. So these thetas are parameterizing the first layer, and then each theta is parameterized by its own set of theta. Its layer is parameterized by its own set of thetas, and then now this whole thing is my preparation for a word that's parameterized by all of these sets of thetas. So these were used by Voite in that Nature paper to do some classification with quantum machine learning, supervised quantum machine learning setup, where they use these things to create kernels for classification. But here we use them to encode the meanings of the states. And in this slide, basically what I want to say is that these specific ansatz have a nice property, which is they're friendly to transpositions. So basically, if you just 180 rotate them, which is transposition in categorical quantum mechanics, all you have to do is just turn it upside down, rotate it, and then basically you just reverse the labelings of the thetas, right? It's just 180 rotation. So reaching the end of the talk, what I want to show you is an explicit example of a diagram, a sentence diagram, which shows its meaning state preparation as reshaped by the first method, which creates this bipartite graph. And I'm going to give some specific values just for the example to these hyperparameters here. And these hyperparameters say how many qubits am I giving to the noun space, that is the dimension, the vector space, the Hilbert space dimension, which is carried in the noun wire. So this is this, and I'm giving it 2 qubits, so it's a 4D state space. So this is 4. To the sentence, I'm giving 1 qubit only, so this is 2D. And D is the depth of the IQP ansatz. So D is this D, and it's basically how many layers am I giving to the preparation of each box, of each word. And if you take this diagram and you draw the quantum circuit that corresponds to it by filling up the boxes with IQP style ansatz, what you get is so something like this is ready to be put on a quantum computer after it goes through a compiler. So the compiler is supposed to minimize this, simplify this diagram, remove swaps, try to fit it on some architecture. For example, this is what IBM's Paris device looks like. It has 27 qubits. This is its connectivity. So the blobs are qubits, and the edges between them are where you can do 2 qubit gates, and the colors are error rates. So you see that 2 qubit gates are the most prone to error, and what a compiler has to do is basically take and try to fit it on this architecture and try to minimize the depth that counted as how many sequential 2 qubit operations I can do before noise comes and kills the whole computation, and then you go home and cry. So this whole talk is about plugging these circuits on a NISQ device, and there's a lot of experimentation that has to be done. But on the other hand, it could also be some sort of quantum machine learning framework where it's also friendly to devices that not only exist today but also will exist in the near future. So maybe like 50 qubits is not enough to do something very, very interesting, but maybe, I don't know, 1,000 is. We'll see in the future. But since I mentioned that we have like only 30 or 50 qubits, maybe you can still do something interesting. And this is what Alex and Giovanni tried to do recently. And basically what they try to do is do some supervised task where you have a bunch of sentences and they are labeled with some true and false labels. and then you try to learn the parameters of the word so that the true and false labels are matched. And basically what you can do then, try to do some question answering. I've written some small blog post on Medium if you're interested, and go check it later. So what you would do is you train the words so that the truth labels are correct, and then Giovanni would ask the quantum computer some question, and then, you know, Chomsky is an anarchist, the quantum computer would say yes, and Alexis would be happy, and then, you know, maybe he would think that communism is better, but whatever. And with that, I want to conclude and say that stay tuned. There's more of this stuff to come. We're experimenting still, and I will end my talk here and thank the organizers again, and ask you if you have any questions.
All right, let's thank Konstantinos. I see there's, oh, I should clap. Hang on, I have to type my clap. There we go. I see that we have one question here. Okay, so Pablo asks, the output state is supposed to be a state representative of the meaning of the sentence. Intuitively, it needs to be of dimension at least noun squared times verb to be rich enough.
Sorry, I think I lost.
Yeah, it's a statement, but it has a question mark at the end. I think he's asking, does the dimension space, or does the sentence space need to have a very high dimension, something like quadratic in the number of nouns to be rich enough?
I see. Yeah. So this is a hyperparameter that depends, basically, as I say it, on what task you're trying to do, and yeah, I think that's how I want to reply to this. It depends on the task of what you're trying to do. So, for example, the simple thing that Alex and Giovanni run, and you can find on this GitHub repo that I showed before. Basically, the sentence space is just a scalar. It's 1D. There's no qubits there. But you can say that the sentence space then encodes a truth value between 0 and 1. Because if you're going around this circuit, you're gonna get a probability between 0 and 1. And then if all you care about is just some binary thing that is encoded in the sentence, then you're fine with a 2D space, even though you have a bunch of nouns and adjectives, and the corpus is big, as we said. It's a good question for generic tasks. Like if you want to have something that is trained, and then like task independently, if that even is possible, I'm not sure. And then you want these trained words to be embedded in some sentence space of high enough dimension so that they can perform in any task you can think of and conceive later. Then I'm not sure how big that sentence space should be.
Mm-hmm. Okay, so John asks, what's the largest sentence you've been able to fit on a physical machine?
All right. So what was it? Alice loves Bob, who is rich, something like this. No sexism comment here. It could be the opposite. But it's something like this, something with a relative pronoun and a transitive verb and an intransitive verb or an adjective. It's this type of sentences. And I think the number of qubits we used for such sentences after reshaping was something of the order of 10 or something like that. Mm-hmm. The depth also was around, well, then it depends on ansatz, but the very simple ansatz we tried, very, very simple, I have to say. They gave C0 depth of, what was it, like 8, around the order of 10, 8 or 12 or something like that. And that is in counting C0s. And that was also on the Singapore device. Because I have to say which device, because every device has different connectivities.
Mm-hmm. Is that, did you say number of C0s or layers of C0s when you say 8?
Layers, yeah. Yeah, because if you can do them in parallel, they count as one.
Okay, yeah. And you didn't get straight noise out of something that was depth 8. There was some signal there.
Yeah.
Uh-huh. Okay, maybe I'll ask one more question and then leave the rest for slacking. Michael Morschot asks, at the start of your NLP pipeline, you represent the association between types and words as a typing function, assigning a pregroup type, TW, to each word in the lexicon.
Yeah.
Actual NLP work on extracting types from corpora shows that, in fact, the lexical ambiguity factor is very high. How does your setup deal with lexical ambiguities, i.e. picking the right pregroup type to get a meaningful derivation?
That's a good question. So ambiguity here in the parser, we don't have it. We don't have the parsing step tied to the meaning step. So it's a good question. It's something that we have to work on later, I think. So we consider the parsing step to be solved in the beginning, and then with a classical parser, and then we just use the mapping to quantum circuits just for the evaluation, and basically, yeah, for the evaluation of the or preparation of the state, or evaluation of, for example, things like sentence similarity. So like if you have a sentence, so this is taken out of Zeng-Coecke. So if you have a sentence being prepared and you want to compare with like the state of, so in the paper it's like kids play ball. Here you have sport, or you don't have sport and you have politics. And you want to see this overlap. The idea is that shape, and then you do this evaluation of this inner product on the quantum computer. But the parsing step, we consider it as a decoupled first step that is supposed to be carried out by classical rules. Let's say it's further work for now.
Okay, let's thank Konstantinos again. Thanks, I'll clap.
Are we still here?